In this lecture we're going to discuss dimensions and units. A dimension is a fundamental defined quantity, and it's not the same as three-dimensional space, for example, that has length and width and height, and we might even add time in there, which is not to say that time and length are not dimensions, but that's not what we're referencing when I say dimensions here. We are going to oftentimes use dimensional analysis to make sure an equation is correct. In other words, if we don't have the correct dimensions, then we know there's a problem with our equation. And so this is going to be very helpful when it comes to analyzing our equations. Units are specific quantities that are attached to each dimension, defined values for each dimension. So here are the first 5 dimensions in the 6th angle we'll talk about here in just a minute. So length is a dimension, and this will include width and height, if you will. So an amount of distance is going to be the beginning of what we call our first dimension. Then the amount or quantity of material, the mass of the material, will be the next dimension. And there's no way of equating length and mass. These are completely different dimensions, and we'll see this for all dimensions. Time is the next dimension. And then current, when we talk about electricity, we're going to talk about the flow of charge. And that's going to be the dimension referred to as current, which is charge per unit time. When we talk about thermodynamics, we'll talk about temperature as a dimension, and we'll see that there's a distinct relationship between temperature and energy. Now, energy is a combination of mass, length, and time, and so temperature is related to those, but it's going to be its own dimension, and we'll use it in equations. Angle is a dimensionless quantity, and this is hugely important because there are some functions which cannot have a dimensioned quantity as the argument of that function. So what is the argument of a function? If I say f of x equals x squared, x is the argument of that function. Now some functions, like f of t equals sine omega t, the argument of sine is omega t. Now this combination is actually going to be dimensionless. The argument of a sine function is generally measured in radians or degrees, and those are dimensionless quantities. Now it turns out t has a dimension, and that is time. And so omega will also have a dimension. That'll be 1 over time. So when I multiply omega times t, I get 1 over time times time, and that's equal to 1. There's no dimension there. So the argument of a trigonometric function must be dimensionless. The same thing is true of a log function. If I say q of r is equal to the log of r, then r cannot have dimension. For example, the log of 5 feet is the same as the log of 60 inches. And yet the log of 5 does not equal the log of 60. So there's no way of using 5 feet in the argument of a logarithmic function. Same thing is holding true of exponents. R of q equals e to the q power. Q must be a dimensionless quantity. Just like e to the 5 feet, e to the 60 inches doesn't make any sense. You can't do it. So some functions, specifically for us, trigonometric functions, logarithmic functions, irregardless of base, and exponential functions, again, irregardless of base, cannot have a dimensioned quantity in its argument. So the first dimension we want to talk about is length. So this is a measure of distance. In the metric system, or what's referred to as the SI system, so that's the same as the metric system. SI stands for Standard International, except it's in French, which I'm not going to try to pronounce. The metric system uses meters as the fundamental or the foundational length. There are other measures like centimeters or millimeters or kilometers, and these are all multiples of the meter. Now the centimeter is 10 to the minus second meters, and this is the only exception to the rule of threes. Everything else, like the millimeters, 10 to the minus third meters, kilometers, 10 to the plus 3 meters, will always have exponents of multiples of 3. 3, negative 3, 6, negative 6, 9, negative 9, etc. So when we're talking about light, the wavelength of light will oftentimes refer to those distances in nanometers. That's 10 to the minus 9th meters. In the imperial system, or the English system, the fundamental unit of length is the foot. There are other units of length, of course. 12 inches equals 1 foot. 3 feet equals 1 yard. And you can see that these lengths are not nice, like 1,000 meters in a kilometer. In fact, there are 5,280 feet in 1 mile. These numbers are very odd, and they're actually based on the number 6, which is a very old system. We still use that sexagesimal system as what it's referred to today. If you look at their 60 minutes in an hour, 60 seconds in a minute, 24 hours in a day, all of these are divisible by 6. Mass is measured in kilograms in the SI system and slugs in the English system. This is also going to be measured in pounds. Now, pounds really isn't a mass. Pounds truly is a force. But we're so used to referring to pounds as a mass that we're going to go ahead and use that on occasion. Although in a physics class, we generally never use pounds. But you might come across it later on in an engineering class where you have to work with the English system because that's what a lot of your customers in the United States are going to use. You'll also hear pounds mass and pounds of force, and it all becomes really quite confusing. So we're going to steer away from that a little bit, and we'll consider 1 slug to be the fundamental unit in the English system for mass. Seconds is the fundamental time unit in both the English system and the metric system, so that's kind of nice. It works about the same in both. And the current is the same again in the metric system as the English system. The ampere is the fundamental unit of current, and the coulomb is the fundamental unit of charge, and again they're very much related. 1 ampere equals 1 coulomb per second. We'll get to that at a much later time. And finally, temperature. In the metric system, the Kelvin temperature scale is used. The Celsius temperature scale is very similar, except the Kelvin scale has a 0 bottom. There is no below 0 on the Kelvin scale. It's what we refer to as an absolute temperature scale. The Celsius scale does have below 0 temperatures. We know that 0 is the freezing point of water on the Celsius scale. In the English system, the Fahrenheit scale is used, and we know the English system has a freezing point of 32 degrees on the Fahrenheit scale. And then there's 0 Fahrenheit, which is really cold, but we can be sub-zero on the Fahrenheit scale. In a similar relationship between Kelvin and Celsius, there's Rankine and Fahrenheit, where the Rankine scale uses the same increments. In other words, from 1 to 2 has a certain size on the Fahrenheit scale. From 1 to 2 on the Rankine scale is the same size. Of course, 1 degree on the Rankine scale is very cold, so 0 is the bottom on the Rankine scale. In my years and years of teaching, I've really never used it except to discuss its existence. Now, when we're doing mathematics with dimension quantities, there are a couple of things that's really important. The mathematical functions of addition and subtraction and the mathematical equality of two values can only exist for terms of the same dimension. For example, let's talk about addition. I can add 4 feet plus 8 feet, and if I do that, I know that I'm going to get 12 feet. So I have a length plus a length, and that gives me a length. That's okay, but I can't add 4 feet plus 8 pounds because that doesn't make any sense. So this is not allowed. I can add two values of the same dimension even if the units are not the same. So you might say 4 feet plus 8 inches, and that's 4 feet 8 inches, not a problem. I could even say 4 feet plus 8 meters and still be fine. That's a valid quantity. I can have a length of rope 4 feet long and a length of rope 8 meters long, and put the two lengths of ropes together, and I will get another length of rope, whatever that value might be. It is a legitimate length. So that's fine. There's no way to set 17 meters equal to 82 kilograms. You can't do it in any way, shape, or form. They're not the same quantity, so you can't set up those equalities. So this is also not allowed. Now this will be really important as we're working with equations, because if I have the left side of an equation and I calculate everything out, I might come up with a dimension that isn't the same as what's on the right-hand side of the equation. And what that tells me is that I've got an error someplace in the equation. Now the standards that we set up when we talk about a meter or a foot, these need to be quantities that are invariable. For example, the speed of light in a vacuum never changes. It's very important what Einstein said, that the speed of light is invariable no matter what the reference frame. We'll get to that maybe in another later lecture. Suffice it to say, the distance light travels in a vacuum in 1 second never changes. Doesn't matter what kind of light it is. As long as it's in a vacuum, the distance it travels in 1 second, is invariable. Whereas something like the size of the king's foot and something of that nature was how we defined a foot way back in the day. That varies. The size of his foot will vary as he changes age or as he changes weight. And so we can't use that as a standard because it's a variable quantity. And I've already talked a little bit about the prefixes or the powers of 3. So again, in the SI system, we're always going to base our units, whether it's mass, length, or time, what have you. Those units will be based on some sort of a standard that is as invariable as we can get it. And we'll see what that means here in just a moment. And then as I go to larger units or smaller units, I'm just going to use powers of 3 to make changes. So I might talk about 1 second, and I might talk about 1 microsecond, and that would be 10 to the minus 6th seconds. Okay, so let's talk about the meter. A long time ago, the meter was 1/10,000,000th of the distance from the North Pole to the equator. Keep in mind, the Earth is not a sphere. It's an oblate spheroid. In other words, it's longer along the equator than it is along the poles. And if I go from the equator to the pole, that's going to be different if I start off in Mexico than if I start off in Africa. So that's not going to work. That is not an invariable quantity. So what we've done is we've defined the meter as the distance light travels in a vacuum in 1/299,792,458th of a second. Now, back when we defined the meter this way, light traveled in 1 second, 299,792,458 point something meters. And what we've done is we've decided, since light is invariable, we'll define the meter based on that. And we didn't want the meter to change very much, so we stuck to 9 digits of accuracy, and I'll talk about significant figures later on in this lecture, so that all of the meter sticks in the world are accurate to within 9 digits, which is more than enough accuracy. When we talk about orders of magnitude, an order of magnitude is based on a power of 10. So if I were to say that my height is 2 orders of magnitude larger than, say, the length of my toe, then what I'm saying is my height is 100 times 2 orders of magnitude, 10 times 10, roughly 100 times the size of my toe. So we're going to talk later on in the course about being close to within an order of magnitude or being way off by several orders of magnitude. Time is defined based on the oscillations of the cesium-133 atom. When the atom makes a certain transition, it gives off light, and that light will oscillate over 9 billion times, you can see the number there, in 1 second. And that's invariable. That's not going to change. As long as it's cesium-133, that light is going to vibrate that many times consistently. And so we define the second as the time it takes for that many oscillations to take place. The important thing here is that this is defined. It's never going to change. Now, mass is problematic. It's very difficult for us to define mass in the same ways that we've defined the other things. And so what we've done, and this has been this way for 100 years, there's a cylinder kept underneath a double bell jar at the International Bureau of Weights and Measures, and that cylinder is defined by international agreement to be 1 kilogram. And so if I am creating a weights and scales company and I need 1 kilogram, I'm going to go to the Bureau of Weights and Measures and I'm going to create a piece of metal and I'm going to balance it against the platinum iridium cylinder that's kept there. And when I do that, I know that that piece of metal that I've created is 1 kilogram. Now keep in mind, if it oxidizes, it's going to gain or lose weight. And so I've got to carefully keep that piece of metal that I've just created constant as I take it back to my company and then create other 1 kilogram masses. Now we can get close to a defined value if we talk about carbon-12. So carbon-12 has 6 protons, 6 neutrons, and 6 electrons. And we've decided to make that have a value of 12 atomic mass units. So we've defined the atomic mass unit based on carbon-12. The problem is we need a lot of carbon atoms to make a kilogram. So it becomes difficult to define beyond the atomic mass unit. So let's talk a little bit about significant digits or significant figures. When I take a measurement, let's say of a block of wood, I might get 16.3 centimeters. What I'm telling you when I give you this number is that I know the length of that block of wood down to 1/10 of a centimeter or 1 millimeter. And so when I look at 1, 6, and 3, This is 3 digits, and so my number is accurate to 3 digits. If I tell you that I am 2 meters tall, I'm being rough in that statement. I could be 1.7 meters, but if I round that off, that's 2 meters. I could be 2.1 meters tall, but if I round that off, that's 2 meters. And so if I only give you 1 digit of accuracy, there's really a lot of leeway for error in the measurement there. But if I stand under a ruler and I happen to be 2 meters tall according to the ruler, I'm probably telling you that I'm 2.0 meters tall, accurate to within 10 centimeters, or even 2.00 meters tall, accurate to within 1 centimeter. Now if I am accurate with that length to 1 centimeter, that's 3 digits of accuracy. So what you'll notice is that these zeros after the decimal place count for digits. If it's a really good ruler, I might even be 2.00 meters tall. That's 4 digits of accuracy. Zeros after the decimal place, if they're not leading zeros, will count. So I might be measuring the time it takes for memory to be loaded onto a chip. That might be something like 0.000000025 seconds. Now when I write that, these zeros do not count for accuracy because these are leading zeros. This number has 2 digits. Now if I said 250, then that would be a third digit. And that would be 3 digits of accuracy. Even though it's a 0, it's not a leading 0, it's a trailing 0 after the decimal place. If I tell you I have $100 in my pocket, that might be $90, it might be $105, that could even be $120, but I've rounded it down to $100. These zeros trail, and there's no decimal place there. So trailing zeros without a decimal place do not count for digits of accuracy. So this has only 1 digit of accuracy. Alright, so it's just 1 digit of accuracy in that number. Now if I said I had $110, now I can't have 120, but I might have 105. I won't have 90, so this is 2 digits of accuracy. Zeros in between, if I say I have $105, then this is 3 digits of accuracy. And that intermediate 0 does count as one of my significant digits. When I do arithmetic, specifically multiplication and division of numbers with significant digits, the final value I work with can have no more digits than the least number of digits I'm working with. So for example, if I said I had 3.77 meters traveled and it took me 5.8 seconds, when I do this calculation, I'm going to get a number. Now, this bottom number is 2 digits of accuracy, and the top number is 3 digits of accuracy. And so the final number that I get when I display that number will only be 2 digits of accuracy. Okay, so when I finish this problem, I get 0.65. Now that actually worked out perfectly, so that's really not the best example. Let me change that a little bit. Let me go to 5.7 seconds. Okay, now my calculator spits out 0.6614035.08772. And since I'm only allowed 2 digits of accuracy, the leading 0 doesn't count. Only the 66 does. I look at the 1 because it's going to tell me whether or not I want to round this 6 up. 1 says don't round it up. So my value would be 0.66. And units are still there, so that's meters per second. So if I'm telling you how fast was that moving, I'm going to tell you it was 0.66 meters per second. Now if I use this number later on, I either want to stick with the 3.77 over 5.7 or use all of these numbers that the calculator gives me. But again, I have to keep in mind that in the end, this number is only 2 significant digits. But don't round off for future calculations. Only round off when you're giving me a value. Okay, if I am going to be doing unit conversions, to convert from one type of unit to another really means multiplication by 1. Let's assume I have a board, and that board is 24 inches long. If I say how many feet long is that board, you're going to tell me 2 feet. If I ask you how you got that number, you're going to say I divided by 12. That's really not what you did. If I physically divide this board by 12, then what I'm going to end up with is 12 little boards, and each of them is going to be 2 inches wide. That's what I mean by dividing the board by 12. What you've really done is you've multiplied by 1. So keep in mind, if I say 24 inches times 1, that equals 24 inches. I haven't changed the length of the board at all. If I say 24 inches times 7 over 7, that's equal to 24 inches. Again, I have not changed the length of the board. If I say 24 inches times r over r, that's 24 inches. I have not changed the length of the board. If I say 24 inches times a over b equals 24 inches, you would say a is equal to b. The numerator equals the denominator. If I take 24 inches and I multiply by 1 foot over 12 inches, I'm multiplying by 1 because the numerator equals the denominator. And if I do that, the inches cancel out, and I'm left with 24 times 1 foot over 12, which is 2 feet. Notice the units stick around. So 24 times 1 is 24, divided by 12 is 2. I get 2 feet. 2 feet is the answer I get when I convert 24 inches into feet. Now, whenever you do unit conversions, be careful of significant digits. Let's try an example. Let's convert 3.0 meters into yards. I start with 3.0 meters. I know that there are 100 centimeters in 1 meter, so that's 1. I know that there are 2.54 centimeters in 1 inch. That's by definition, so that's very important because that means 2.54 centimeters is defined. That's not 3 digits of accuracy, that's infinite number of digits of accuracy. I know that 1 yard has 36 inches. Again, the numerator equals the denominator. So I notice the meters cancel out, the centimeters cancel out, and the inches cancel out. And I'm left with 3.0 times 100 divided by 1 times 1 divided by 2.54, again that's an infinite number of digits there, times 1 over 36. And if I work all that out, my calculator says 3.2808398995. And then I look at the original number, that's 2 digits of accuracy, so that's 3.2, but the 8 says round that up, and so this would be 3.3 yards. Because again, the yard is the only unit left over in the end. Alright, let's try the next one. 17.5 kilograms. Now my book says that there are 2.2046 pounds in 1 kilogram. Now notice the way I've written that. The numerator equals the denominator, but the kilograms don't cancel. So even though this is correct, it isn't useful. So I'm going to turn that upside down. So 1 kilogram equals 2.2046 pounds. Now this is not defined, this is rounded off. So that's a little different than the 2.54 centimeters to 1 inch. That's one of the few defined conversions from metric to English. So if I take 2.2046 and multiply by 17.5, I get 38.581 pounds because the kilograms have canceled out. But 17.5 is 3 digits, so there's my 3 digits, but the 8 says round that up. So 38.6 pounds is 17.5 kilograms. Now if I want to convert that to slugs, I'm going to use that 38.58, but I'll multiply, and I know that 1 pound is the same as 0.031081 slugs. And so I get 1.199 slugs, but I've got still 3 digits of accuracy, so there's my 3 digits, but the 9 says round that off, and that's going to be 1.20 slugs. Okay, let's try one more example. I define a fortnight as 2 weeks, so that's a length of time, and a furlong is a distance, which is equal to 660 feet. So if I am walking at 2.33 meters per second, I'm interested in how fast I'm walking in furlongs per fortnight. And so what I'm going to do is I'm going to convert the meters into furlongs, that's length to length, and I'm going to convert the seconds into fortnights, converting from time to time. So again, I have 1 meter, 100 centimeters, 2.54 centimeters is 1 inch, 12 inches is 1 foot, and 660 feet is 1 furlong. And you'll notice the meters cancel, the centimeters cancel, the inches cancel, and the feet cancel, and I'm left with furlongs, which is what I want, furlongs in the numerator. Now let's tackle the denominator. I have seconds in the denominator, so 3,600 seconds is 1 hour. All of these are defined so far. There are 24 hours in 1 day, and there are 14 days in 1 fortnight. And again, the seconds will cancel, the hours will cancel, the days will cancel, and I'm just left with fortnights. Now let's look at the numbers. 2.33, 100 over 1, 1 over 2.54, 1 over 12, 1 over 660, 3,600 over 1, 24 over 1, and 14 over 1. And unit-wise, I'm only left with furlongs and fortnights. And my calculator says 14010.0214745. That's furlongs per fortnight. This number is 3 digits, and so that brings me to there. The one says do not round up. And so I have 14,000 furlongs per fortnight. Now this number looks like 2 digits. The only way I can really show that there's 3 digits is to write this as 1.40 times 10 to the 4th furlongs per fortnight. In other words, I have to use scientific notation to really get that expressed correctly.